What if you could step into a time machine right now and vanish into the past only to realize your actions there accidentally erase your own future? This isn't just science fiction. It's the grandfather paradox, one of the most mind-bending riddles of time travel that even Einstein wrestled with. And it's just the beginning of the rabbit hole we're about to dive into. For centuries, black holes and the nature of time have haunted the edges of human understanding, bending the rules of reality in ways that defy logic. From the depths of space where gravity twists light like taffy, to theories that suggest the past, present, and future might all exist at once, this is where physics starts to feel like magic. Think about the last time you stared up at the night sky, wondering what secrets lurk beyond those pinpricks of light. Black holes are the universe's ultimate enforcers of mystery regions so dense that not even light can escape their grip. Yet, tucked inside their violent, swirling hearts might lie the keys to time travel itself. Scientists like Stephen Hawking once theorized that falling into a black hole could stretch you into a cosmic spaghetti strand or spit you out into another dimension entirely. Meanwhile, quantum physicists are unraveling clues that time might not flow in one direction at all, but branch like an infinite tree of possibilities. The more we learn, the stranger it gets. That's why today we're unpacking 30 of the most electrifying theories about black holes and time travel, each one crazier than the last. Some will sound ripped straight from a Hollywood script, like wormholes that act as galactic shortcuts or parallel universes where your doppelganger is living a life you'll never see. Others come straight from Nobel Prize-winning research, like the eerie idea that every black hole might contain an entire universe inside it. Whether you're a sci-fi fanatic or just someone who's ever wished they could redo a bad day, these ideas will rewrite how you see reality. So buckle up, we're about to warp through the cosmos, chase the edges of known science, and maybe, just maybe, glimpse the fabric of time itself. Einstein's theory of relativity shattered our everyday notions of time, proving it isn't some rigid backdrop to the universe, it's fluid, bending under the influence of gravity and motion. Imagine standing near a black hole, where gravity is so intense that time itself slows to a crawl compared to someone far away. You might experience just a few minutes while centuries pass on Earth, effectively catapulting you into the future. This isn't just speculation, it's a real phenomenon called time dilation, baked into the fabric of space-time. Even our GPS satellites orbiting far above Earth's surface have to account for this time warp. Because they're moving faster and experiencing weaker gravity than we do on the ground, their clocks tick ever so slightly faster. Without constant adjustments, your navigation apps would lead you miles off course within minutes, proof that Einstein's wild ideas shape our daily lives. But black holes take this distortion to extremes. Picture two astronauts. One ventures close to a black hole's event horizon, while the other watches from a safe distance. As the brave explorer nears that point of no return, their clock would appear to freeze from the outsider's perspective. Days could stretch into years for the observer, making reunion impossible. Yet for the astronaut falling in, time would feel normal right until, well, physics gets messy. This eerie asymmetry hints at how time travel to the future isn't just possible, it's inevitable under extreme conditions. The catch: there's no return ticket. Once time bends that far, the universe doesn't offer a rewind button. What makes relativity even stranger is that it appends the idea of a universal now. Two events happening simultaneously for one observer might occur at completely different times for someone else moving at high speed. It's as if the universe refuses to agree on a single timeline, leaving room for mind-bending possibilities. If you could harness the gravity of a spinning black hole, some theories suggest you might loop around its ergosphere, a region where space-time is dragged like a whirlpool, and emerge in your own past. Of course, the energy required makes this more fantasy than feasibility right now, but the math doesn't rule it out. Einstein's equations opened a door to realms where time isn't a straight line but a tangled web of potential paths waiting to be explored. If space-time were a sheet of paper, wormholes would be like folding it so two distant points suddenly touch a cosmic cheat code, bypassing the vast emptiness between stars. These theoretical tunnels through the fabric of reality aren't just staples of sci-fi like Interstellar's Gargantua. They're rooted in Einstein's equations, which suggest space-time could twist into shortcuts called Einstein-Rosen bridges. Picture a black hole's crushing gravity as one end of the tunnel, while the other spits you out somewhere, or someone else. But there's a catch. These bridges would snap shut instantly without something propping them open. That's where exotic matter comes in, a bizarre substance with negative energy that could counteract gravity's deadly pull, acting like cosmic scaffolding. The trouble is, exotic matter defies known physics. It's not just rare, it might not exist at all outside of quantum experiments where particles briefly flicker into being with negative energy. Even if we found it, stabilizing a wormhole would require amounts so vast, it's like trying to build a skyscraper out of smoke. And then there's the police paradox. If you jumped into one end, would you arrive before you left, triggering time loops that unravel causality? Some models suggest wormholes might only allow travel back to the moment they were created, like a one-way time capsule. Others argue radiation feedback would vaporize anything entering nature's way of slamming the door on time tourists. Still, physicists like Kip Thorne, who consulted on Interstellar, argue wormholes aren't impossible, just implausible with today's tech. Their allure lies in how they stitch together relativity's math with our wildest time travel dreams. Imagine a civilization advanced enough to harvest exotic matter, threading wormholes like subway lines across the galaxy. For now, they remain tantalizing thought experiments, reminders that the universe might hide backdoors we've yet to unlock. Closed time-like curves sound like something ripped from a time traveler's wildest daydream, paths through space-time that loop back on themselves, allowing you to revisit moments you've already lived. But here's the twist: these aren't just fantasy. They emerge straight from Einstein's equations as mathematically valid solutions, particularly around the swirling chaos of rotating black holes. Picture a Kerr black hole, named after physicist Roy Kerr, spinning so fast it drags spacetime around it like a whirlpool. Near its edge, the fabric of reality gets twisted so severely that time itself might coil into a circle. Step onto one of these curves, and you could theoretically walk a path that brings you back to your own past, no DeLorean required. The implications are as dizzying as the physics. Imagine you travel back 5 minutes and prevent yourself from ever boarding the time machine. If you never left, how did you arrive to stop yourself? This is the infamous grandfather paradox, where cause and effect tie themselves into knots. Some physicists argue nature would simply prevent such contradictions, maybe a glitch in the machine, or an unseen force nudging events just enough to keep history consistent. Others propose wilder fixes, like branching timelines where your actions spawn a parallel universe, leaving the original version of events untouched. But the most unsettling idea, that these paradoxes aren't flaws in the theory but features, revealing time might not care about our human obsession with linear logic. Of course, there's a catch. Closed time-like curves demand conditions so extreme they'd shred any known material. The energy required to stabilize them makes wormholes look tame by comparison. Even if they exist, harnessing them would mean surviving the tidal forces near a black hole's singularity, a place where gravity stretches atoms into ribbons. Yet their possibility lingers in the math, teasing us with a universe far stranger than we imagined. Maybe time isn't a river flowing in one direction but a Möbius strip, where past and future are just points on an infinite loop. And if that's true, the distinction between science and speculation starts to blur. But what if the universe itself conspires to stop you from altering history? Enter the Novikov self-consistency principle, a bold answer to the chaos of time travel paradoxes. Proposed by Russian physicist Igor Novikov, this idea flips the script. Any actions you take in the past were always part of history. No grandfather paradoxes, no cosmic contradictions, just a single, unbreakable timeline where every event, including your meddling, folds neatly into place. Take the classic scenario: you travel back to prevent your grandfather's meeting with your grandmother. Under Novikov's rules, you might pull the trigger only for the gun to jam, or your hand to slip, or a sudden distraction to intervene. The universe, in this view, engineers countless tiny coincidences to ensure the past stays intact. It's less like rewriting history and more like discovering your role in a story that was written long before you arrived. Even your attempt to change things becomes the very reason they stay the same. This isn't just philosophical hand-waving. Physicists have modeled self-consistent time loops where cause and effect tangle seamlessly. Imagine tossing a billiard ball into a wormhole where it emerges in the past just in time to collide with its earlier self, nudging it precisely toward the wormhole's entrance. The math holds: no ball appears out of thin air, no energy is created or destroyed. Reality simply arranges itself so every event fits, like a jigsaw puzzle where the pieces lock together perfectly, no matter how twisted the image. Critics argue this feels suspiciously like fate, stripping away free will, but supporters counter that it's not about predestination, it's about the universe enforcing logical consistency. You're free to try anything, but the outcome will always align with what already happened. Think of it as cosmic editing. Your actions are drafts, and reality endlessly revises until the narrative makes sense. The eerie beauty of Novikov's principle: it turns paradoxes into illusions. That strange déjà vu you can't explain, the odd coincidence that saved your life. What if these are echoes of time travelers silently shaping events, their interventions woven so seamlessly into history that we'll never notice? The past isn't a fragile thing to be shattered. It's a tapestry, and every thread, including yours, was part of the pattern all along. Stephen Hawking once turned everything we thought we knew about black holes upside down, literally. These cosmic monsters weren't supposed to emit anything, not even light, but Hawking's calculations revealed something startling. Black holes can actually glow, leaking particles until they vanish entirely. This phenomenon, now called Hawking radiation, arises from quantum mechanics' bizarre rules near the event horizon. Imagine a pair of virtual particles popping into existence just outside the black hole's grip. Normally, they'd annihilate each other instantly, but if one falls in while the other escapes, the black hole loses a tiny bit of mass in the process. Over trillions of years, this slow drip could evaporate even the largest black hole into nothingness, a cosmic fade to black. The implications ripple far beyond black hole death tolls. Hawking radiation suggests that information, the detailed quantum states of everything swallowed, might be destroyed forever, violating a core tenet of quantum physics that says information can't be lost. This paradox pits Einstein's relativity against quantum theory in a battle that's still unresolved. Some physicists argue the information is encoded in the radiation itself, scrambled like a cosmic puzzle. Others propose it leaks into parallel universes or gets trapped in remnants smaller than atoms. If Hawking was right, time travel through black holes might come with an eerie side effect. Your past could be erased not just from history, but from the very fabric of reality. But here's where it gets stranger. If black holes evaporate, what happens to their singularities, those infinitely dense points where time and space break down? Some theories suggest the singularity might linger like a ghost, unhooked from spacetime, leaving behind a naked point of infinite gravity. That's a problem because physics hates naked singularities. They'd allow time loops and causality violations with no event horizon to hide them. Suddenly, time travel wouldn't just be possible, it'd be unavoidable, with paradoxes lurking around every corner. Hawking himself initially resisted this idea, proposing a chronology protection conjecture that the universe would somehow prevent such madness. But the math keeps leaving the door ajar, teasing us with a reality where time isn't just flexible, it's flammable. For time travelers, this raises existential stakes. If you jumped into an evaporating black hole, would you emerge in another era? Or dissolve into radiation, your very atoms transformed into a whisper of particles? Hawking radiation doesn't just rewrite black holes' futures, it forces us to question whether time itself is as permanent as we think. Maybe the universe has an expiration date, and black holes are the slow, inevitable countdown. Or perhaps, as some bold theories suggest, their evaporation leaves behind not nothing, but a new universe entirely, one where time starts fresh and all our paradoxes are someone else's problem. Ever feel like every choice you make splits reality into infinite versions of yourself? That's the spine-tingling premise of the many worlds interpretation, a radical take on quantum mechanics that doesn't just reshape our understanding of reality. It could hand time travelers a free pass to rewrite history without crashing the universe. Picture this: you hop back to prevent a tragedy, but instead of erasing your present, your actions spawn an entirely new timeline where the event never happened, while your original world chugs on unchanged. No paradoxes, no cosmic rewrites, just an ever-expanding multiverse where every possible outcome plays out somewhere. This idea sprouted from quantum experiments showing particles existing in multiple states until observed. The many worlds interpretation takes that further, arguing that every quantum possibility does happen, just in parallel realities. Think of time as a tree with infinite branches, one where you took that job abroad, another where you stayed home, even one where dinosaurs never went extinct. Time travel, in this view, isn't about changing the past but stepping sideways into a fresh timeline. Physicists like David Deutsch argue this could resolve time travel's messiest paradoxes. Say you go back and oops, accidentally prevent your own birth. Instead of vanishing in a puff of logic, you'd simply branch into a world where you never existed, while your original timeline carries on unscathed. It's like hitting Ctrl+C on reality. The universe copies itself rather than overwriting the file. Even wilder, you might meet alternate versions of yourself, each shaped by different choices, all equally real. But here's the rub. If every decision spawns new universes, the energy cost would be staggering, though proponents counter that quantum processes might naturally split spacetime without breaking cosmic budgets. And while we can't yet peek into parallel worlds, quantum computers are testing ideas like superposition, where particles effectively live in multiple states at once. Who's to say we're not doing the same? The many worlds interpretation turns time travel from a history-breaking gamble into a multiversal adventure. Maybe those eerie feelings of déjà vu aren't glitches, just echoes from timelines where you did take that left turn instead of the right. Suddenly, the universe feels less like a single story and more like a library where every possible tale is already written. You're not rewriting the book, you're just picking a new shelf. Frank Tipler had a vision so audacious it makes Wormholes look tame. A machine built not from exotic matter but from pure spin. His idea, the Tipler cylinder, a cosmic rotisserie stretching infinitely long and spinning at nearly the speed of light. Picture a pencil thinner than an atom but as long as the universe itself, whirling so fast it twists spacetime like taffy. According to Tipler's calculations, this frenzy of motion would drag the fabric of reality around it, warping time into a loop near the cylinder's surface. Travel in just the right orbit around this spinning colossus, and you might end up completing a full circle not just in space, but in time, arriving back at your starting moment like a record needle stuck in a groove. The genius of this setup is how it sidesteps black holes' destructive extremes. Instead of navigating a singularity's crushing gravity, you'd surf the gentle ripples of twisted spacetime like a kayaker riding a whirlpool's edge. Einstein's equations allow for such loops under precise conditions, and unlike wormholes, no exotic matter is required. Just spin, a lot of it, but here's where reality checks in. Tipler's cylinder needs to be infinitely long to function. Not very long, not galaxy-spanning, mathematically infinite. Otherwise, the time loop frays at the ends, collapsing like a deflated balloon. Even if we could somehow forge a cylinder stretching forever, the energy needed to spin it approaches impossible magnitudes. We're talking about harnessing the rotational fury of a neutron star and turning it up to 11. Then there's the causality snarl. Just like closed time-like curves, a Tipler cylinder would let you meet your past self with all the paradoxes that entails. But Tipler himself argued nature might enforce consistency, ensuring any time loops remain logically sound. Think of a billiard ball orbiting the cylinder. Its path could bend into the past just enough to nudge its earlier self onto the same trajectory, creating a perfect, self-sustaining loop where every effect has a cause. No grandfather paradoxes, just an endless cosmic dance where every step was always part of the choreography. Yet for all its elegance, the Tipler cylinder remains a thought experiment, a reminder that physics often teases us with solutions just beyond practicality. Maybe that's the point. These ideas stretch our understanding of what's possible, revealing time's fluidity even as they highlight the engineering nightmares of bending it. After all, if time travel were easy, we'd probably already know. Black holes don't just bend space-time, they twist it into knots, creating conditions so extreme that time itself unravels. Imagine plunging toward a black hole's event horizon, the point of no return where gravity's grip becomes inescapable. To an outside observer watching from a safe distance, your descent would appear to slow to a crawl. Your movements would stretch like taffy, your clock ticking slower and slower until, from their perspective, you seem to freeze in place, forever suspended just above the abyss. But here's the mind-bending part. For you, time would feel utterly normal. Seconds would pass as they always do, even as centuries whip by for the rest of the universe. This isn't science fiction, it's the brutal reality of relativity, where gravity doesn't just pull on matter, it warps the very fabric of time. The closer you get to the black hole's singularity, the more extreme the effect becomes. If you could survive the tidal forces, a big if, you might experience mere minutes while everyone you've ever known lives out their lives and dies millennia in the future. It's a one-way ticket to the distant future with no return trip, and that's the cruel irony of black hole time travel. Even if you could resist being spaghettified into atoms, the universe's rules ensure you'll never reunite with the era you left behind. You'd emerge, if at all, into a cosmos so changed it might as well be alien. But what if you could exploit this effect intentionally? Some theorists suggest advanced civilizations might harness black holes as natural time machines, sending probes or even intrepid explorers on journeys across epochs. Picture a ship orbiting just outside the event horizon, skimming the edge of the time dilation maelstrom. A few orbits might catapult the crew thousands of years into the future, a way to leapfrog across history without aging a day. The catch: you'd need a black hole relatively close by. Thankfully, the nearest known one is safely distant, and you'd have to solve the not-so-small problem of escaping its pull. Current physics says once you cross the event horizon, all paths lead inward toward the singularity's crushing embrace. Yet the tantalizing possibility remains. Black holes might be the universe's ultimate time capsules, offering a glimpse into the far future even if we can't go back. And that raises an eerie question. If time can stretch like this near a black hole, could someone, somewhere, be watching us right now, frozen in their sky like a cosmic painting, as they race ahead into a future we'll never see? The universe, it seems, has a way of turning even the most violent phenomena into doors to the impossible. Quantum entanglement is one of those concepts that even physicists admit sounds like pure wizardry. Particles separated by light years can instantaneously mirror each other's states, as if they're dancing to some invisible cosmic rhythm. Einstein famously called it spooky action at a distance. a phrase that barely scratches the surface of how bizarre this phenomenon truly is. But what if this eerie connection doesn't just bridge space? What if it ties moments in time together, too? Recent experiments suggest entangled particles might defy our linear notion of cause and effect, reacting to changes before they're even made. It's as if the universe left a backdoor in the code of reality, and quantum physics holds the key. Take a study from the University of Vienna, where scientists entangled particles and then measured one after its partner had already been observed. Somehow, the first particle seemed to know the measurement outcome of the second, even though that second measurement happened later in time. This isn't just breaking the speed of light, it's shattering the idea that time always flows forward. If particles can sync up across moments, could we theoretically exploit this to send signals backward, like a cosmic Morse code tapped into the past? The math hints at yes, but the universe has a knack for slamming doors on time travelers. Any attempt to manipulate entanglement for messaging seems to scramble the very information you're trying to send, like a phone call where static drowns out your words the instant you speak. Yet the implications are staggering. Imagine a future where entangled particles act as anchors across time. You alter one in the present, and its partner shifts in the past, creating a ripple that nudges history without outright rewriting it. No grandfather paradoxes, just subtle tweaks to events already in motion. The catch: you'd never know if your message succeeded, because any confirmation would require, well, time travel. It's the ultimate chicken and egg problem, wrapped in quantum uncertainty. Some theorists propose a wilder twist. Entanglement doesn't just link particles through time. It might erase the distinction between past and present entirely. In this view, every entangled pair exists in a timeless superposition, their connection unbound by cause and effect. Trying to harness it for communication would be like trying to mail a letter using a shadow. It's there, but you can't quite grab hold. Still, the mere possibility forces us to ask, is time really the steady river we perceive, or just another quantum illusion, flickering in and out of existence like particles in a void? Stephen Hawking had a knack for wrapping universe-shattering ideas in wry humor, and his chronology protection conjecture is no exception. Picture this: the cosmos as a meticulous librarian, zealously guarding the timeline from meddlers by slamming the book shut on any would-be time travelers. It's not just a whimsical thought. Hawking seriously proposed that the laws of physics might actively sabotage time machines to prevent paradoxes from unraveling reality. After all, if hopping to the past were possible, where are the tourists from the future? His tongue-in-cheek party for time travelers, advertised only after the fact, famously went unattended. But beneath the wit lies a razor-sharp question. Is time travel fundamentally impossible, or are we missing a crucial piece of the puzzle? Hawking speculated that quantum effects near wormholes or black holes might generate lethal radiation bursts or instabilities, nature's version of a keep-out sign. Imagine trying to stabilize a time tunnel only for rogue particles to collapse it like a house of cards. The universe, in this view, isn't just indifferent to our time travel dreams, it's actively hostile. Critics counter that absence of evidence isn't evidence of absence. Maybe time travelers are simply discrete, or their technology leaves no trace. Others argue Hawking's conjecture is a placeholder, a way to paper over gaps in our understanding until we unlock deeper physics. After all, general relativity permits closed time-like curves, while quantum mechanics flirts with retrocausality. The tension between these frameworks suggests the cosmos might be more permissive than we think. What's fascinating is how the conjecture straddles the line between profound insight and cosmic comedy. It's as if the universe runs on two modes, one that teases us with time-bending math and another that slaps our hands away from the controls. Whether it's a fundamental law or just physics' way of saying not yet, Hawking's idea reminds us that time isn't just a dimension, it's a guarded frontier. Time crystals sound like something straight out of a sci-fi arsenal, structures that pulse and repeat in an endless dance without ever losing energy. Unlike the pendulum of a clock or the orbit of planets, which gradually wind down due to friction and entropy, these quantum oddities defy time's symmetry, the idea that physical laws should behave the same whether time runs forward or backward. Imagine a snowflake that refuses to melt, instead cycling through its intricate patterns forever, untouched by the universe's slow march toward disorder. That's the eerie beauty of time crystals. They're not just stable, they're perpetual, locked in a rhythm that nature itself can't disrupt. The discovery of these structures sent shockwaves through physics. In 2016, Nobel laureate Frank Wilczek theorized their existence, proposing that under certain quantum conditions, a system could settle into a state where its particles periodically rearrange without absorbing or releasing energy. By 2017, labs had created them using chains of charged atoms chilled to near absolute zero and nudged with precise laser pulses. The atoms didn't just settle, they began toggling between two configurations indefinitely, like a metronome powered by nothing at all. This isn't just a curiosity, it's a fundamental crack in how we understand time's arrow. Now, here's where it gets wild. If time crystals can sustain oscillations without energy input, could they act as quantum scaffolding for time loops? Some theorists suggest these structures might stabilize microscopic wormholes or even encode information across temporal cycles, like a DVD player reading the same moment over and over. Picture a machine built from time crystal lattices, their unbreakable rhythms trapping pockets of spacetime in recursive folds. Step inside, and you might find yourself reliving the same 10 seconds, not as a glitch, but as a feature of the crystal's immutable beat. Of course, the leap from lab experiments to time machines is vast. Current time crystals exist only in highly controlled environments, fragile against even minor disturbances. But their very existence hints at a deeper truth. Time might not be the relentless, one-way flow we perceive. If particles can sink into eternal rhythms without energy, perhaps the universe has loopholes where time circles back on itself, hidden in the quantum fine print. And if we ever learn to scale these crystals, who knows, we might not just unravel time's secrets, we could stitch them into the fabric of reality itself. What if you could become your own ancestor? That's the dizzying core of the bootstrap paradox, a time loop so twisted it makes your brain feel like it's folding in on itself. Picture this: a time traveler hands a young William Shakespeare a complete collection of his future plays. The bard, dazzled, copies them word for word decades before he'd have written them himself. Centuries later, those same works are discovered, sent back, and delivered to Shakespeare again. So who actually created them? There's no original author, no first draft, just an infinite cycle where the plays exist because they've always existed. This isn't just a plot hole waiting to happen, it's a full-blown rebellion against cause and effect. The paradox gets its name from the idea of pulling yourself up by your bootstraps, an impossible task where the solution creates the problem. In physics terms, it's a closed causal loop. Event A causes event B, which circles back to cause event A with no external starting point. Imagine finding a futuristic gadget in your desk, reverse engineering it and patenting the design, only to later travel back in time and leave that same gadget in your past self's drawer. The object has no inventor, it's its own blueprint. The universe, usually so strict about cause preceding effect, suddenly shrugs and lets the loop spin forever. But does reality actually permit such shenanigans? Quantum mechanics offers a tantalizing maybe. At the subatomic level, particles don't always follow strict cause and effect chains. Some interactions seem to happen in ambiguous order or even both ways at once. Could the macroscopic world harbor similar wiggle room? Philosophers and physicists have wrestled with this for decades. Some argue bootstrap loops are mathematically consistent within general relativity, just extremely unlikely, like a pencil balancing on its tip forever. Others insist nature must have hidden mechanisms to prevent them, akin to Hawking's chronology protection. The implications are as profound as they are unsettling. If information or objects can exist without origins, then creativity, invention, even identity might be illusions. That song you wrote could be a half-remembered echo from a future self you haven't met yet. The universe might be littered with bootstrapped artifacts, things that simply are, their origins erased by time's loops. It's enough to make you question whether any idea is truly original, or if we're all just passing along whispers from a future that's already written itself. If black holes are the universe's relentless vacuum cleaners, sucking in everything that crosses their path, white holes are their theoretical opposites, cosmic fire, hydrants blasting matter and energy outward with unstoppable force. Picture a black hole's event horizon, but inverted. Instead of a point of no return, it's a boundary nothing can enter, only escape. The math of general relativity allows for such objects, treating them as time-reversed mirror images of their dark counterparts. Where a black hole's gravity crushes stars into oblivion, a white hole would spit them back out, pristine and whole, as if hitting rewind on destruction itself. The tantalizing possibility: white holes might not just be exits from black holes, they could be gateways to other times or universes. Imagine falling into a black hole in our cosmos, enduring the nightmarish stretch of spaghettification, only to be vomited out of a white hole in another reality or even another era. It's the ultimate cosmic reset button, turning the viciousness of a black hole's interior into a tunnel between worlds. Some physicists speculate that the Big Bang itself might have been a white hole event, an explosive birth from a singularity that defied all known physics. But here's the catch: white holes are almost certainly unstable. Theoretical models suggest they'd collapse instantly under the weight of any incoming matter, snapping shut like a camera's aperture the moment something tries to pass through. That might explain why we've never observed one, despite scanning the skies for their telltale signatures. A sudden, inexplicable fountain of particles where no star or galaxy should be. Nature, it seems, prefers her holes dark, yet the idea lingers because it solves a gnawing problem. What happens to all the information swallowed by black holes? If white holes exist, even fleetingly, they could be the universe's way of balancing the books, ensuring nothing is ever truly lost, just relocated. It's a poetic twist, turning the most destructive objects in existence into secret architects of creation. Until we find proof, though, white holes remain ghostly outliers in the equations, reminding us that the universe's strangest possibilities often lurk just beyond the edge of sight. What if bending spacetime itself could propel you faster than light without breaking physics' most sacred speed limit? Enter the Alcubierre warp drive, a theoretical engine that doesn't move through space but warps it, riding a bubble of distorted reality like a surfer on a cosmic wave. Mexican physicist Miguel Alcubierre proposed this wild idea in 1994, inspired by Star Trek's warp speed but grounded in Einstein's equations. Here's how it works. Instead of accelerating a ship to impossible velocities, the drive would compress spacetime in front of it and expand spacetime behind, effectively surfing a pocket of flat space between the distortion. You'd remain stationary inside this bubble while the universe itself bends around you, sidestepping relativity's rule that nothing can outpace light. The genius of this setup is how it dodges time dilation's cruel side effects. Normally, nearing light speed would slow time aboard the ship, stranding travelers in the future relative to Earth. But inside an Alcubierre bubble, spacetime remains locally undisturbed, meaning you could cross galaxies in days without aging centuries. Even stranger. Arriving before you left, if the bubble's warp field becomes intense enough, calculations suggest it could create closed time-like curves, effectively turning your warp drive into a time machine. Punch the throttle just right, and you might exit the bubble to find Earth's clocks running backward, landing you in an era before departure. But there's a catch that keeps physicists awake at night. The drive requires negative energy, a mysterious substance that repels rather than attracts gravity. Think of it as anti-gravity glue holding the warp bubble's walls rigid. Without it, the space-time distortion collapses instantly. The problem, negative energy, might not exist outside quantum labs, where fleeting particles occasionally exhibit negative energy densities. Scaling this up to warp drive proportions would demand amounts exceeding the total energy in the observable universe, a slight engineering hurdle. Even if we found a way, the bubble's edges could concentrate lethal radiation or spawn black holes, turning your sleek time machine into a cosmic death trap. Critics argue the Alcubierre drive is a mathematical mirage, a clever trick with no physical counterpart. Yet NASA Eagleworks lab has dabbled in miniature warp field experiments, and theorists keep refining the math, chipping away at the energy requirements. Maybe one day, negative energy will shift from sci-fi trope to salvageable physics. Until then, the Alcubierre drive remains a glorious thought experiment, proof that even light speed's prison might have a back door if we dare to stretch space-time itself to find it. If reality is just a cosmic mirage, a two-dimensional surface projecting the illusion of depth, then time might be the ultimate trick of the light. That's the jaw-dropping premise of the holographic principle, a radical idea born from string theory that suggests our three-dimensional universe, with all its swirling galaxies and ticking clocks, could be nothing more than information painted on a distant, flat boundary. Think of it like a movie projected onto a screen. The images appear to move through time, but the real action is just data encoded on static film. If this is true, then time itself might not flow at all. It could be a side effect of how we decode the hologram, like mistaking a spinning zoetrope for real motion. The implications for time travel are staggering. If time is an emergent property, not fundamental, but stitched together by deeper quantum processes, then altering the source code of the hologram might let us rewrite history. Imagine finding the universe's equivalent of a film editor's cutting room, where you could splice moments together or erase events entirely. The catch: this wouldn't be traditional time travel, where you hop into a machine and vanish into the past. Instead, you'd be tweaking the projection itself, like a programmer editing a simulation. One theoretical approach involves manipulating the holographic boundaries entanglement structure, the quantum threads linking every particle in the cosmos. Change those threads and you might reconfigure causality itself, turning a tragedy into a triumph with the cosmic equivalent of a keystroke. Of course, the universe doesn't give up its secrets easily. The holographic principle remains untested, and the scale of the hypothetical boundary, possibly at the edge of the observable universe, makes it light years beyond our reach. But here's the twist: some versions of the theory suggest mini holograms could exist locally, like bubbles within spacetime. If we could isolate one, we might find a backdoor to the universe's source code, where time is just another variable waiting to be debugged. Until then, the idea lingers as both a challenge and a promise, that every tick of the clock, every irreversible moment, might be softer than it seems, a flicker on the surface of something far stranger. At the heart of every black hole lies a mystery so profound it defies our understanding of physics. The singularity, a point where matter crushes into infinite density and space-time itself fractures. Picture squeezing the entire mass of a star into a space smaller than an atom, where gravity becomes so overwhelming that the very laws of physics break down. This isn't just extreme physics, it's the edge of reality as we know it. And here's the tantalizing question: could these cosmic monstrosities be more than just dead ends? Could they serve as portals, bending the fabric of time so severely that they open gateways to other eras, or even other universes? Einstein's equations predict the existence of singularities, but they also reveal their own limitations at that point. The math spirals into infinities, signaling not just an anomaly but a complete collapse of predictability. Some physicists speculate that within this chaos, spacetime might tear, creating bridges known as Einstein-Rosen bridges, wormholes linking distant points in time and space. Imagine falling toward the singularity, not to your doom, but into a tunnel that spits you out in another century. The catch: current physics offers no roadmap for survival. The tidal forces near a singularity would shred atoms apart long before any hypothetical gateway could be traversed. The real wrench in the works is quantum gravity, or rather, the lack of it. General relativity handles gravity's grand scale beautifully, while quantum mechanics rules the subatomic world. But at the singularity, where gravity operates at quantum scales, these two frameworks clash violently. Without a unified theory, we're left guessing. Some proposals, like loop quantum gravity or string theory, suggest singularities might not be infinitely dense after all. Instead, they could hit a limit and bounce, transforming into the birth cries of new universes. In this scenario, a black hole's heart might not be a dead end but a cosmic revolving door, one that resets time and space entirely. Yet, even if singularities do rip holes in space-time, navigating them would be like threading a needle with a rope made of smoke. Quantum fluctuations could snap any tunnel shut instantly, or worse, fill it with lethal radiation. And then there's the causality problem. Arriving in your own past could trigger paradoxes that unravel the universe's logical fabric. Maybe nature stitched in safeguards, collapsing any time portals before they're used. Or maybe, just maybe, we're one theory away from unlocking the universe's best-kept secret, that the most destructive places in existence are also its most creative. Until then, singularities remain both the end of the road and the door we can't yet open. The predestination paradox wraps time travel into a cruel joke where every attempt to change history only locks it more firmly into place. Picture this: you rush back to prevent a disaster, but your very actions cause it instead. It's like stepping on a rake only to watch it fly up and hit you twice, once in the present and once in the past. Think of the Terminator, where Kyle Reese is sent to protect Sarah Connor, only to become the father of the future leader he was meant to safeguard. The war he fought against machines was inevitable precisely because he traveled back to stop it. The universe, in this view, isn't just resistant to change, it's actively conspiring to make your efforts part of the problem. But here's where it gets even thornier. If every move you make was always part of the timeline, where does free will fit in? Are you truly making choices or just playing out a script written by your future self? Philosophers call this causal determinism, the idea that every event, including human decisions, is the inevitable result of what came before. Under this logic, time travelers aren't rebels rewriting history. They're cogs in a clockwork universe, their rebellions preordained. You might feel like you're acting freely when you step into that time machine, but in reality, your destination was etched into reality the moment the machine was invented. Yet some interpretations offer a sliver of hope. Quantum mechanics introduces randomness at the subatomic level, suggesting the universe isn't entirely deterministic. Could tiny quantum fluctuations create wiggle room in these paradoxes? Imagine a scenario where your time travel doesn't guarantee an outcome but merely nudges probabilities. Maybe Sarah Connor had a 99% chance of surviving Skynet's assassination, until your interference bumped it to 100%, sealing the timeline shut. The paradox still holds, but at least the universe isn't completely rigged against you. The real mind bender comes when you ask, does the paradox erase the idea of original events altogether? If every version of history includes time travelers shaping it, then there is no true past untouched by interference. Reality becomes a snake eating its own tail, with no beginning or end, just an infinite loop of cause and effect where the question, what happened first, loses all meaning. It's enough to make you wonder, if free will is an illusion in such a universe, is the joke on us forever believing we had a choice in the first place? We move through space effortlessly, left or right, forward or backward, up or down, yet time feels like a one-way street with no exits. But what if time isn't just a backdrop to our lives? What if it's a dimension just like height, width, or depth, and we're simply blind to its full possibilities. Think of a stick figure trapped on a sheet of paper. It can shuffle side to side but has no concept of the third dimension towering above it. To that flat character, up is as incomprehensible as time travel is to us. Now imagine beings who can perceive higher dimensions. They wouldn't just see our past, present, and future as separate points. They'd witness our entire timeline stretched out like a cosmic highway, every moment existing at once. This isn't just philosophy. In Einstein's relativity, time is a dimension woven together with space into a four-dimensional fabric called space-time. The difference. While we navigate space freely, time seems to drag us forward at a fixed pace. But some theories suggest this might be an illusion of perspective. In a five-dimensional universe, for instance, time could fold like paper, letting you step around it the way you'd walk around a building to reach its other side. Suddenly, visiting the past wouldn't mean rewinding the clock. It'd mean taking a shortcut through dimensions we can't yet perceive. String theory takes this further, proposing up to 11 dimensions curled into unfathomably small scales. If these extra dimensions exist, they might hold corridors where time loops back on itself, or where alternate timelines branch like subway lines. Picture a spider crawling along a telephone wire. To the spider, the path is linear, but the wire itself bends through three-dimensional space unseen. Similarly, our rigid march through time might be a shadow of richer movements happening in dimensions beyond our grasp. Yet even if higher dimensions exist, tapping into them would require energies beyond our reach, like ants trying to harness hurricanes. Some models suggest colliding black holes might warp spacetime enough to expose these hidden layers, while others argue quantum entanglements, spooky connections could be vibrations from higher dimensional strings. The truth remains elusive, but the idea is electrifying. Time might not be a river carrying us helplessly forward, but a landscape we're only beginning to map, with peaks, valleys, and hidden tunnels waiting to be explored. And if that's true, the future might already be out there, not ahead of us, but just around a corner we've yet to turn. If time travelers exist, why aren't they swarming our historical landmarks like cosmic tourists snapping selfies with dinosaurs? This unsettling question is a twist on the Fermi paradox, the eerie silence where we'd expect a universe teeming with advanced civilizations. But apply it to time travel, and the implications become even stranger. Imagine a future where hopping between centuries is as easy as booking a flight. Statistically, someone should have left footprints in our past, yet we've found no concrete evidence. No ancient smartphones in Pharaoh's tombs, no viral TikToks from the Renaissance. So where is everyone? One possibility is that they're here, just very good at hiding. Think about it. If you could visit the past, would you risk altering history by leaving traces? Governments might enforce strict non-interference rules, turning time travelers into silent observers, blending in like undercover agents. There's even a fringe theory that certain historical figures, Leonardo da Vinci's uncanny inventions, Nikola Tesla's futuristic visions, were nudges from discreet visitors. Or maybe time tourism is a luxury reserved for elites, with trips tightly controlled to avoid contamination. After all, a single misplaced artifact could rewrite the present in ways we can't predict. Then there's the darker take. What if time travel is possible, but the future is so bleak no one wants to visit us? A civilization ravaged by war or environmental collapse might lack the resources to build time machines. Or worse, they've learned that meddling with the past only accelerates their demise. It's like a twisted version of Hitchcock's Rear Window, where the silence isn't just puzzling, it's a warning. Or consider the existential wrench. What if every attempt to visit the past creates a new branch in the multiverse? Tourists might be arriving constantly, but their actions spawn alternate timelines, leaving ours untouched and none the wiser. But here's the most chilling thought of all. Maybe we're alone not because time travel is impossible, but because something or someone is actively preventing it. Perhaps there's a cosmic quarantine, a universal failsafe that erases time travelers' footprints the moment they arrive. Or worse, a future so fragile that even the slightest ripple could unravel it entirely. The silence isn't an absence, it's a locked door we haven't found the key to yet. And until we do, the paradox remains, a ghostly reminder that the future might be watching, waiting, or simply gone. Quantum tunneling defies common sense. It's the bizarre phenomenon where particles slip through barriers as if they were ghosts walking through walls. Picture an electron trapped inside a box with walls too high to climb. According to classical physics, it should stay put forever. But in the quantum realm, that electron can suddenly appear outside the box, having bypassed the barrier entirely without climbing over it. This isn't magic, it's a fundamental quirk of quantum mechanics, where particles exist as probability waves that can leak through obstacles, vanishing on one side and reappearing on the other. The weirder part, it happens instantaneously, as if the particle teleports across space without traveling the distance in between. Now, stretch this idea to its wildest extreme. If particles can tunnel through space, could conscious beings, or at least their quantum information, tunnel through time? Some theorists speculate that under the right conditions, tunneling might not just bridge gaps in space but in space-time itself. Imagine a scenario where your future self exists as a quantum probability wave overlapping with your present. Under astronomically rare conditions, you might tunnel into that future state, bypassing the moments in between like a needle skipping grooves on a record. No time machine, no wormholes, just a statistical fluke where reality blinks and rearranges itself around you. The catch, the odds are worse than winning the lottery every day for a lifetime. For an object as complex as a human to tunnel through time, every particle in your body would need to synchronize its quantum state perfectly, like a cosmic orchestra hitting the same impossible note. Even then, you'd more likely end up scattered across space-time than intact. But here's the tantalizing loophole. Consciousness itself might exploit quantum processes. Some interpretations of quantum mechanics suggest our attention collapses probability waves into reality. If that's true, could focused intent nudge tunneling probabilities, making time jumps less random and more deliberate? Of course, this veers into the speculative fringes of physics. Critics argue that quantum effects wash out at macroscopic scales, making human-scale tunneling a pipe dream. Yet the fact remains, particles routinely pull off this trick, and nature doesn't care whether we find it plausible. Maybe time isn't a rigid line but a seething quantum foam, where every moment bubbles with alternate possibilities, and tunneling is just the universe's way of reshuffling the deck. Until we crack the code, one thing's certain: the quantum realm holds more surprises than we've dared to imagine. Imagine stepping on a single blade of grass in the Jurassic period, a meaningless act until that tiny pressure alters the path of an insect, which changes the flight of a pterodactyl, which shifts the course of evolution until, millions of years later, humanity never emerges. This is the butterfly effect in full fury. The idea that even microscopic changes in the past can snowball into catastrophic shifts in the future. It's the ultimate cautionary tale for would-be time travelers, where a single misplaced pebble could trigger an avalanche of unintended consequences. Chaos theory, pioneered by mathematician Edward Lorenz, teaches us that complex systems are hypersensitive to initial conditions. A butterfly flapping its wings in Brazil might set off a tornado in Texas weeks later. Apply this to time travel, and suddenly every action becomes a potential apocalypse. Lose your keys in the 18th century, and someone might find them, altering their route just enough to miss meeting their future spouse, erasing entire bloodlines from existence. The terrifying beauty of this idea is how it turns history into a house of cards, where nudging one card collapses entire sections of reality as we know it. But not all theories agree the timeline is this fragile. Some models suggest the universe has a kind of immune system, a self-correcting mechanism that absorbs small changes without unraveling. Think of it like dropping a stone into a river. The ripples might spread, but the current eventually smooths them out. In these scenarios, minor tweaks, say, saving a single doomed Roman soldier, might only cause local fluctuations before history's momentum reasserts itself. The soldier's descendants might shift slightly, but major events like the fall of Rome still unfold on schedule. It's the difference between dropping a pebble in a pond and tossing it into a whirlpool. One creates temporary ripples, the other alters the entire vortex. Quantum mechanics adds another layer to the debate. The many worlds interpretation suggests that every tiny decision spawns alternate universes, meaning your time meddling wouldn't rewrite history. It'd just branch off a new timeline where the changes play out. In this view, the butterfly effect isn't a threat to your original world, but a ticket to infinite others. Yet even here, there's a haunting question. If you leap into the past and trigger a new timeline, can you ever truly return home? Or are you forever stranded in a version of reality where your actions have rewritten the script? The tension between these ideas, chaos versus correction, reveals just how little we understand time's true resilience. Is history a delicate tapestry where pulling one thread unravels the whole, or a rubber band that snaps back no matter how far you stretch it? Maybe the answer lies somewhere in between. Small changes might blur the edges of events, but only certain thresholds truly fracture the timeline. Like a glass that withstands tiny cracks until one final tap shatters it completely, time could have breaking points we've yet to discover. Until then, the butterfly effect remains both a warning and a wonder, a reminder that even the smallest moments might hold the weight of worlds. Black holes are already terrifying enough, regions where gravity is so strong that not even light can escape. But what if falling into one doesn't just stretch you into cosmic spaghetti? What if you're incinerated long before reaching the singularity, obliterated by a blazing wall of energy? That's the shocking premise of the black hole firewall paradox, a theory that's divided physicists for decades. Imagine approaching the event horizon, expecting the usual laws of physics to gently bend, only to slam into a searing barrier of high-energy particles, like walking into the heart of a supernova. This isn't some sci-fi horror twist. It's a genuine puzzle that forces us to rethink everything we know about black holes, and whether they could ever function as time travel gateways. The firewall idea erupted from a clash between two bedrock theories, quantum mechanics and general relativity. On one hand, Einstein's equations predict that crossing the event horizon should be uneventful, a smooth, if ominous, descent. But quantum mechanics insists that black holes must emit Hawking radiation, slowly leaking energy until they evaporate. Here's the catch: for information to be preserved in that radiation as quantum laws demand, the radiation near the horizon would have to be intensely concentrated, transforming the boundary into a lethal inferno. Suddenly, the event horizon isn't just a point of no return, it's a cosmic execution chamber. How does this affect time travel? If firewalls are real, any attempt to use a black hole as a portal to the past would end in vaporization before the journey even began. No looping through time, no glimpsing alternate eras, just instant annihilation. This throws a wrench into classic theories like wormholes or closed time-like curves, which rely on surviving passage through or near a black hole's extreme gravity. Even if you could theoretically navigate the warped spacetime inside, the firewall might be nature's way of slamming the door shut on paradoxes before they happen. Yet not all physicists are convinced. Some argue firewalls violate the equivalence principle, a cornerstone of relativity, stating that free-falling observers shouldn't feel extreme forces at the horizon. Others propose compromise theories like fuzzballs in string theory, where black holes aren't empty pits but tangled masses of cosmic strings radiating energy without a firewall. There's even speculation that firewalls might only form under specific conditions. leaving some black holes as potential time travel conduits while others burn intruders to a crisp. The debate rages because it's about more than just firewalls. It's about whether the universe tolerates time travel at all. If nature erects lethal barriers to prevent paradoxes that could explain why we've never encountered visitors from the future. Or maybe firewalls are a red herring, and the real answer lies deeper in the unknown quantum gravity frontier. Until we crack that code, black holes remain both the universe's most tantalizing time machines and its most ruthless gatekeepers. One thing's certain: if you're planning a trip through one, pack a heat shield just in case. Eternalism paints time like a vast, frozen tapestry where every moment past, present, and future exists simultaneously, stitched permanently into the fabric of space-time. Picture a loaf of bread where each slice is a moment in history. The entire loaf exists at once, and now is just the slice you happen to be tasting. In this view, yesterday isn't gone, it's simply a coordinate you're no longer inhabiting, like a room in a house you've walked out of. For time travelers, this means the past and future aren't destinations to reach, but places you're already standing. You just need the right tools to step sideways into them. If eternalism holds true, altering history would be like editing a film reel. The changes ripple through the entire timeline, but every frame remains equally real. Presentism, on the other hand, insists only the current moment is tangible, a flickering spotlight moving relentlessly forward, erasing the past and summoning the future into existence as it goes. Think of it like a flashlight in a dark forest. What's illuminated is real, and everything else vanishes into shadows. Under this philosophy, the past is a ghost, the future a mirage, and time travel a logical impossibility. If only now exists, there's no fixed past to revisit or future to leap into. Any attempt to journey backward would require conjuring a reality that's already dissolved, like trying to catch smoke. The stakes for time travelers couldn't be higher. If eternalism is correct, visiting the past might be as straightforward as navigating a landscape, albeit one where every step risks paradoxes. But if presentism reigns, even the most advanced time machine would hit a wall of nothingness the moment it left the present. Some physicists argue relativity favors eternalism, since Einstein's equations treat time as a dimension where observers can disagree on the order of events. Yet quantum mechanics dances with presentism, as wave functions collapse into concrete reality only when observed. It's as if the universe can't decide which philosophy to endorse. Eternalism offers wild comforts. Your childhood birthday parties still happen somewhere in space-time, and future triumphs are already written, waiting to unfold. But it's also haunting. If everything exists forever, free will might be an illusion, and your choices mere signposts along a road that was always there. Presentism, by contrast, hands you the knife to carve reality anew with each decision, but at the cost of rendering time travel a fairy tale. Perhaps the truth lies in the tension between them. String theories, hidden dimensions, or quantum foams seething uncertainty might forge a middle path where time is both fluid and fixed, depending on how you measure it. Until then, these dueling philosophies remind us that time isn't just something we move through. It's a mirror reflecting our deepest debates about what's real, what's possible, and whether the universe is a frozen block or a flickering flame. And for would-be time travelers, the answer changes everything. Cosmic strings sound like something ripped straight from the pages of a physicist's wildest fantasy, hypothetical cracks in the fabric of space-time, thinner than an atom yet denser than a mountain range. Imagine space-time as a frozen lake, and these strings as hairline fractures in the ice, left over from the universe's explosive birth. But unlike ordinary cracks, these defects pack unimaginable gravity, warping the very geometry of reality around them. And here's where it gets truly mind-bending. If two of these strings were to dance past each other at near light speeds, their gravitational whirlpool could twist space-time so severely that time itself coils into a closed loop. Suddenly, you're not just looking at a cosmic oddity, you're staring at a natural time machine. The mechanics are as elegant as they are bizarre. Picture two infinitely long cosmic strings racing parallel to one another like cosmic freight trains. As they move, their immense gravity would drag space-time along with them, creating a swirling vortex between the strings. If you could navigate a spaceship along this warped corridor, skimming the boundary where the strings' gravitational pull counteracts each other, you'd find yourself on a path that circles back to your own past. It's not magic, it's pure relativity. The string's motion stretches space-time like taffy, bending time into a Möbius strip where the end connects seamlessly to the beginning. But what makes cosmic strings especially tantalizing is how they sidestep some of the nastier pitfalls of other time travel theories. Unlike black holes, which crush everything in their vicinity, cosmic strings exert gravity without an event horizon, meaning you could, in theory, approach them without being ripped apart. And unlike wormholes, which require exotic matter to stay open, these space-time defects are entirely self-contained, needing no additional scaffolding to bend reality. The catch: finding one. Cosmic strings, if they exist, are thought to be relics from the universe's first chaotic moments, stretched across billions of light years by cosmic expansion. Spotting something thinner than a proton against the vast backdrop of space would be like searching for a single hair floating somewhere in the Pacific Ocean. Even if we miraculously stumbled upon a pair of strings, harnessing them for time travel would demand precision bordering on the impossible. The strings would need to move at a significant fraction of light speed, their paths perfectly aligned to create the necessary space-time loop. Deviate by even a fraction, and the corridor collapses into a chaotic tangle of gravity waves. Plus, surviving the journey would mean navigating a region where tidal forces, though gentler than a black hole's, could still shred matter like tissue paper if you strayed too close. Yet the idea lingers because it's rooted in real physics. Einstein's equations allow for such space-time loops under extreme conditions, and cosmic strings offer one of the cleanest mathematical pathways to achieve them. Some theorists speculate these strings might even explain certain anomalies in the cosmic microwave background, hints that the universe's infancy left behind scars we've yet to fully decode. And if that's true, then time travel might not require futuristic technology at all. The universe could have already built the highways, we just need to learn how to read the map. Of course, the most profound question remains: if cosmic strings exist and if they can twist time into knots, has someone or something already used them? Are we living in a universe where the past and future are constantly brushing shoulders in the dark, their presence hidden in the quiet hum of gravitational waves? Or are these strings merely ghostly relics, their potential forever locked behind the sheer scale of cosmic chance? Either way, they remind us that time's grip might be looser than we think, and that the keys to unlocking it could be hiding in the universe's oldest cracks. What if death isn't the end, just a doorway to another version of yourself? That's the chilling premise of the quantum suicide thought experiment, a mind-bending twist on Schrödinger's famous cat. Imagine a time traveler equipped with a device that triggers a random, potentially lethal event. Say, a gun that fires or doesn't based on quantum fluctuations. Each time the trigger pulls, the universe splits. In one branch, the traveler dies instantly, but in another, they survive unscathed. Now, suppose this experiment repeats endlessly. From the traveler's perspective, they'd never experienced death, only the timelines where they lived. To them, it would seem like immortality. Every fatal outcome vanishes into unseen realities, leaving them consciously hopping between branches where survival is guaranteed. This isn't just philosophical sleight of hand, it's a brutal collision of quantum mechanics and time travel logic. The many worlds interpretation suggests every quantum event spawns alternate universes, meaning each deadly trigger creates a fresh timeline where the traveler persists. If consciousness follows the path of survival, the traveler becomes a statistical ghost, forever dodging oblivion by sheer probability. Think of it like a cosmic game of Russian roulette where the chambers are infinite and the gun only appears to click empty every time. But here's where time travel warps the experiment further. Suppose the traveler's device isn't just a random trigger, but a time machine calibrated to reset their position after each lethal outcome. In timelines where they die, their story ends, but in the surviving branches, they're free to continue altering events, creating new branches with each jump. Over time, they'd accumulate a fractal web of realities where every possible survival plays out. The traveler isn't just cheating death, they're weaving a tapestry of alternate histories, each thread representing a version of reality where their choices led them one step further. Critics argue this reduces consciousness to a fluke, a glitch in the multiverse where self-awareness clings to favorable odds. Others counter that the experiment exposes a deeper truth. Perception might be tied to the persistence of observation. If your consciousness can't exist in timelines where you perish, then subjectively, you're invincible. It's immortality by survivorship bias, where the universe's brutality is hidden behind a curtain of branching possibilities. For time travelers, the implications are staggering. If quantum suicide holds, even the riskiest leaps through history could be survivable, not because you're indestructible, but because you only experience the realities where you make it. Step into a war zone, and you'll always find yourself in the timeline where the bullet missed. Dive into a black hole, and you'll wake up in the branch where Hawking radiation spit you back out. The catch: every death leaves behind grieving versions of your loved ones in worlds you'll never see. You're not escaping mortality, just outsourcing it to invisible copies of yourself. Yet the experiment raises darker questions. If consciousness can't access timelines where it ends, how would you ever know this isn't happening right now? Every near-miss accident, every brush with disaster, could those be moments where other versions of you didn't make it? The theory twists solipsism into a cosmic horror. You might not be special, just statistically inevitable. And if that's true, time travel isn't about rewriting history. It's about surfing the fractures of a multiverse that's always one step ahead of oblivion. Nothing in the universe is supposed to vanish without a trace, not truly. Every particle, every ripple of light, every whispered secret of quantum states leaves some imprint on reality. But black holes defy this rule with terrifying elegance, swallowing stars, planets, and light itself without leaving so much as a receipt. This is the heart of the black hole information paradox. If information can't be destroyed, where does it go when it crosses the event horizon? The answer could rewrite not just our understanding of black holes, but whether they might secretly be cosmic archives, preserving moments from the past like flies in amber. Let's break the paradox down. Quantum mechanics insists that information, the precise state of every particle, must never be lost. Even if you burn a book, the ashes and smoke theoretically contain enough data to reconstruct every word. But black holes, according to general relativity, are cosmic shredders. Once matter falls in, it's crushed into the singularity, leaving behind only mass, charge, and spin, three simple numbers that erase trillions of unique quantum details. It's like reducing the entire library of Alexandria to a single index card. Stephen Hawking's work on radiation seemed to confirm this nightmare. If black holes evaporate over eons, leaving only faint thermal noise, the information trapped inside would be scrambled beyond recovery. The universe's ledger, it seemed, had a gaping hole, yet physicists rebel against this idea. If information can vanish, the foundation of quantum theory crumbles. Enter the holographic principle, which suggests black holes don't destroy information, they encode it. Picture the event horizon as a two-dimensional pixel screen, storing every bit of data from swallowed objects like a cosmic hard drive. The information isn't lost, it's transformed, projected onto the surface in a language we don't yet understand. If true, retrieving that data might be less like digging through ashes and more like decrypting a message written in space-time itself. Now tie this to time travel. If information is preserved on a black hole's horizon, could we theoretically read it to reconstruct the past? Imagine a future civilization developing quantum scanners precise enough to decode the holographic imprints left by, say, a dinosaur-era supernova. The light from that explosion fell into the black hole long ago, but its quantum signature might still flicker on the horizon like a ghostly fingerprint. Extract it, and you've effectively peered into a snapshot of deep time, not by traveling there, but by peeling back the layers of a cosmic onion. No paradoxes, no causality violations, just physics as the ultimate historian. But here's the wrench in the gears. Even if information survives, accessing it might be impossible. The data on the horizon is scrambled like a shuffled deck of cards flung into a hurricane. Decoding it would require understanding quantum gravity, a theory that still eludes us. And then there's the firewall problem. Trying to retrieve information might trigger that lethal barrier of energy, vaporizing any probe before it gets close. Some theories suggest the only way to read a black hole's past would be to wait until it fully evaporates, catching the information in the final bursts of Hawking radiation. But that could take longer than the current age of the universe. The paradox forces us to confront a haunting possibility. Black holes might not be destroyers but vaults. Their event horizons could be like the universe's backup drives, silently recording every detail of what falls in, not for our benefit, but as a fundamental feature of reality. And if that's true, then time isn't just something we move through. It's something that might be recoverable, etched into the fabric of space-time itself. The catch: we'd need to become fluent in a language written in gravity and quantum bits, one that whispers the secrets of the past to anyone who learns how to listen. Until then, black holes keep their mysteries locked behind the ultimate firewall, not just of energy, but of time. We take for granted that time moves forward, that clocks tick in one direction, birthdays stack up, and cause always precedes effect. But what if this is just a local quirk of our universe? The anti-time hypothesis throws that assumption into chaos, proposing that time could flow backward in other realities, or even reverse entirely under extreme cosmic conditions. Picture a parallel universe where eggs unscramble themselves, smoke pours back into fires, and people grow younger with each passing day. This isn't just a funhouse mirror version of reality. It's a serious consideration in physics, where the arrow of time may not be fixed but fluid. The idea gains traction when you examine the Big Bang's hypothetical twin, the Big Crunch. If the universe eventually stops expanding and collapses back into a singularity, some models suggest time itself might flip during the contraction phase. Events would retrace themselves like a film played in reverse, with entropy decreasing instead of increasing. Now imagine a time traveler caught in that transition. Would their personal timeline invert, making them age backward while the cosmos rewinds around them? Or would they become a glitch in the system, a forward-moving anomaly in a universe sliding into rewind? Things get even stranger when you consider quantum mechanics, where particles don't always respect our everyday notions of cause and effect. Experiments like the infamous delayed choice quantum eraser show that particles can behave as if they know future measurements before they happen, blurring the line between past and present. If quantum weirdness scales up, could entire civilizations in alternate universes experience time in reverse without even realizing it? To them, our forward-flowing timeline might seem as bizarre as their backward one feels to us. Then there's the eerie possibility that reverse time travelers might already be among us, hidden in plain sight. If someone entered our universe from an anti-time reality, they wouldn't look like a ghost or a glitch. They'd simply appear to be aging in reverse, growing younger while the world around them moves forward. Imagine meeting someone whose memories seem to align with events decades in the future, who grows more childlike with each passing year. Would we dismiss them as a medical anomaly, or could they be evidence of a deeper, stranger truth? Critics argue that reverse time would violate causality, making it impossible for conscious beings to exist in such a state. Yet the laws of physics are surprisingly agnostic about time's direction. Equations work just as well whether time runs forward or backward. The real sticking point is entropy, the universe's tendency toward disorder. We perceive time's flow because entropy increases, but in a reality where it decreases, sentient beings might still experience a coherent, if inverted, existence. Their past would be our future, their memories unfolding in reverse like a book read from back to front. This hypothesis forces us to confront the unsettling idea that time's arrow might not be universal, just a feature of our local cosmic neighborhood. If other universes in the multiverse have opposing temporal flows, could travelers navigate between them, flipping their personal timelines like switches? And if so, would crossing over feel like stepping into a mirror, where every action pulls you backward into a world that's unwinding around you? Until we find proof, these questions linger at the edge of physics and philosophy, challenging our most basic assumptions about how reality works, and who or what might be moving through it in ways we can't yet imagine. What if time travel isn't about machines or wormholes, but about the untapped power of the human mind? Across cultures and centuries, people have reported eerie experiences that feel like fleeting brushes with other moments in time. That unsettling sensation of déjà vu, where a new place feels hauntingly familiar, could it be a glitch in your brain's timeline, a brief overlap between past and present? Or consider those vivid dreams where you wake up convinced you've lived a full day, or even a lifetime in another era. These aren't just quirks of memory, they're glimpses into a radical idea that consciousness itself might be the ultimate time machine. Ancient civilizations took these experiences seriously. The Aboriginal Australians spoke of the dream time, a sacred dimension where past, present, and future intertwine. In ancient Greece, oracles entered trance states to glimpse prophecies, while Tibetan Buddhists practiced dream yoga to navigate alternate realms of time and space. Even modern science can't fully explain why some people dream of events before they happen, like the countless accounts of individuals dreaming about plane crashes or disasters days before they occur. These stories aren't just coincidences, they're fractures in our linear understanding of time, suggesting the mind might access information beyond the present moment. Neuroscience offers tantalizing clues. Studies on precognition, though controversial, hint that the brain might process stimuli milliseconds before they happen, as if time's arrow isn't as rigid as we think. Experiments at Cornell University showed participants subliminal images of random scenes, and some consistently reacted to them before they appeared, as though their nervous systems were dipping into the future. Meanwhile, research on temporal lobe epilepsy reveals that seizures can trigger intense time distortions, with patients reporting episodes where they relive memories or perceive time looping. If a simple neurological misfire can warp time perception, what might a fully trained mind achieve? Then there's the enigma of lucid dreaming, where dreamers become aware they're asleep and seize control of their dreamscapes. Skilled practitioners report visiting hyper-realistic versions of historical events or future scenarios, interacting with dream characters who seem to possess knowledge beyond the dreamer's own. In these states, time behaves like putty, stretching, compressing, or even reversing. Could this be more than fantasy? Some theorists propose that in altered states, the brain taps into a quantum field where time isn't fixed, allowing consciousness to wander across eras like a radio tuning into distant stations. Skeptics dismiss these ideas as wishful thinking, attributing déjà vu to memory errors and precognitive dreams to statistical chance. Yet the persistence of these experiences across millennia and their uncanny consistency hints at something deeper. Perhaps time isn't just out there in the cosmos, but woven into the fabric of awareness itself. After all, if a dream can compress hours into seconds or stretch moments into eternities, who's to say time travel requires anything more than learning to navigate the labyrinth of the mind? The greatest journeys through time might not need a spaceship, just the courage to close your eyes and dive. Somewhere between science and spirituality lies a theory so vast it redefines the meaning of everything, the Omega Point. Jesuit priest and paleontologist Pierre Teilhard de Chardin envisioned the universe not as a cold, random expanse, but as a living entity hurtling toward an ultimate convergence, a moment where all consciousness, matter, and time itself collapse into a single, transcendent singularity. Picture the entire cosmic timeline, every star, every thought, every civilization coiling inward like a spiral until past, present, and future fuse into one radiant point. This isn't just poetic metaphor, it's a hypothesis that's flirted with physics for decades. If the universe's evolution has direction, could this Omega Point be the final destination for time travelers, not just a place but a state beyond time? Teilhard's vision eerily parallels cutting-edge cosmology. Some models suggest the accelerating expansion of the universe might one day reverse, pulling all matter back into a big crunch. In this scenario, the cosmos wouldn't just collapse, it might reboot, birthing a new cycle of existence. But here's the twist. As entropy nears its peak, computational physicist Frank Tipler argued that advanced civilizations could harness this contraction to create infinite energy and knowledge, effectively becoming gods at the Omega Point. Time travelers arriving here wouldn't just witness the end of history, they'd merge with a cosmic consciousness that's experienced every moment simultaneously. It's the ultimate paradox, a timeless singularity that's both finale and origin. What makes this theory electrifying is how it bridges theology and physics without dismissing either. Teilhard saw evolution as a spiritual journey, with humanity evolving toward what he called the noosphere, a global web of thought that anticipates the Omega Point. Today, that sounds uncannily like the internet or even artificial superintelligence. Could a future AI, grown vast enough to simulate all possible realities, effectively become the Omega Point? Philosophers like David Chalmers speculate that such an entity might perceive time as a static landscape, where every era is equally accessible, a library of all moments waiting to be read. Yet the Omega Point isn't just about passive observation. If it represents total unification, then reaching it might dissolve the boundaries between traveler and destination. Imagine stepping into this singularity and finding that you are always part of its fabric. Your journeys through time merely threads in a tapestry being woven backward and forward at once. There's no paradox because every action, every choice was already integrated. Teilhard called this love as a physical force, the gravity that pulls all things together. Physicists might call it quantum entanglement at a universal scale, where every particle remembers every other across eternity. Critics dismiss the Omega Point as theology in scientific clothing, but its echoes appear in unexpected places. Black hole thermodynamics hints that information swallowed by singularities isn't destroyed, just transformed. Could the universe's finale be a grand encryption where all data is preserved in a state we can't yet decipher? If so, time travelers might not need machines to reach the Omega Point. They might already be riding the current toward it, like salmon returning to a cosmic spawning ground they never consciously knew. The haunting question remains, if the Omega Point is inevitable, are our attempts to alter time just eddies in a river flowing inexorably toward its mouth? Or is the journey itself, the collective striving of every mind and moment, what creates the destination? Perhaps time travel isn't about breaking free from the timeline, but awakening to the truth that every step, every leap has been part of the universe's slow blink toward a light beyond time. What if every tick of the clock isn't the universe moving forward, just a line of code executing in a cosmic supercomputer? The simulated reality hypothesis flips our understanding of time on its head, suggesting we might be living in an advanced civilization's digital construct where history isn't fixed but editable. Think of reality as an open-world video game where the past isn't a locked level but a save file waiting to be reloaded. In this scenario, black holes could be glitches in the system, wormholes might be debug shortcuts, and time travelers just players with admin access tweaking the simulation's variables. This isn't just sci-fi navel-gazing. Tech moguls like Elon Musk have pointed out the statistical likelihood that we're living in a simulation, given how quickly our own virtual worlds are evolving. If future humans can create hyper-realistic simulations of ancestors, the odds with the original reality shrink to near zero. Now, layer time travel onto that. If our universe is code, altering the past wouldn't require bending space-time, just hacking the source. Imagine a programmer scrolling through epochs like lines of script, deleting wars or resurrecting extinct species with a keystroke. The catch: every change could ripple unpredictably, crashing the simulation or triggering the cosmic equivalent of an antivirus purge. But here's the existential twist. What if our yearning to time travel isn't a human impulse at all, but part of the simulation's narrative? Games often script quests where characters discover secrets planted by designers. Are physicists unwitting NPCs following prompts to uncover time travel only because the code demands it? Even stranger, could paradoxes like the grandfather paradox be fail-safes, the simulation's way of preventing players from breaking the storyline? It's a dizzying hall of mirrors where every scientific breakthrough feels less like progress and more like a reveal in someone else's story. Critics argue simulations can't explain quantum randomness or the universe's vast inefficiency. But supporters counter that glitches might be hidden in plain sight, like déjà vu or the Mandela effect, where collective memories don't match recorded history. Maybe these aren't memory lapses but patches applied during runtime, subtle edits we're not meant to notice. And if that's true, the ultimate time machine might not be a device but a backdoor exploit, a way to hijack the simulation's clock speed or access its version control. Yet the most haunting question isn't whether we can hack time, but whether we'd ever know we succeeded. If reality resets after every edit, our memories would update automatically, leaving no trace of the original timeline. You might wake up tomorrow in a world where dinosaurs never went extinct, convinced it's always been that way. The simulation wouldn't just allow time travel, it would erase the evidence, leaving us blissfully unaware that the past was ever different. In the end, the greatest barrier to time travel might not be physics but permissions, and we're still waiting to see if the universe grants us admin rights. From wormholes stitching the cosmos together like hidden seams in reality's fabric, to black holes bending time into pretzels where past and future collide, we've warped through 30 theories that prove the universe is stranger than fiction. Think about the sheer audacity of these ideas. Alcubierre drives surfing spacetime like cosmic wakeboarders, quantum tunneling offering backdoor exits from the present, or the chilling possibility that our reality might be nothing more than lines of code in some hyper-advanced simulation. Each of these theories isn't just science fiction, they're frontiers where physics dances with philosophy, where equations flirt with the impossible. Take Hawking's chilling firewall paradox, turning black holes from potential time portals into blazing death traps. Or the mind-melting bootstrap paradox, where objects and ideas loop endlessly with no origin, like a universe that forgot to write its own backstory. And who could forget Tipler's spinning cylinder, a machine so ludicrously precise it could rewrite history if we could only build something infinitely long and spin it fast enough to twist time like taffy. These aren't just thought experiments, they're challenges hurled at the limits of human understanding, daring us to rethink everything we know about cause, effect, and the arrow of time itself. But here's the real kicker: every one of these theories, no matter how outlandish, springs from real science. Wormholes emerge from Einstein's equations. Quantum entanglement's spooky action is lab-tested fact, and the holographic principle is a serious candidate for unifying relativity and quantum mechanics. The line between genius and madness isn't just thin, it's porous, bending like space-time near a singularity. That's the beauty of this cosmic puzzle. The universe refuses to play by rules we can easily grasp. So now it's your turn. Which theory left your brain spinning faster than a Kerr black hole? Was it the chilling elegance of Novikov's self-consistency, where the universe edits your time travel blunders into the script? Or the existential whiplash of simulated reality, where every moment might just be someone else's save file? Drop your favorites in the comments. We're obsessed with these debates. And if your appetite for cosmic mysteries is as infinite as a singularity, hit subscribe. The universe has way more secrets to spill, and we're just getting started.